Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to kind of go back to blazars, but specifically microblazars. Now before I do that, in case you haven't seen any of the other videos, I'm kind of going to recap or just go over what galaxies are, and then blazars, quasars, and then into the microblazars, but also microquasars as well, because they're kind of like the same sort of thing. So if you haven't kind of caught my other videos, or you're not familiar with galaxies in general, these are massive systems of stars, gas, dust, dark matter. They're held together by gravity, and there's a whole variety of different sorts of galaxies. This one here is a spiral disk-like galaxy, and depending on the type of galaxy, they have different ratios of stars. Some don't have much gas, some have lots of gas. Same with the dust, dark matter. It depends on the type of galaxy, but they're predominantly made of this sort of stuff. Some of them actually rotate, some of them don't, but again, that's a topic for a different video. But these are massive structures that have billions of stars in, and obviously other stuff as well. So a variety of different sizes. So here I've kind of got some disk-like galaxies. There are elliptical galaxies which are more spherical-like. They don't necessarily have a huge net rotation. The movement of the stars within is a bit more random. So think of kind of like a cloud of gas, really, I suppose, except they're not gas, it's individual stars. So you've got a whole variety of different shapes, sizes. So galaxies are not just one type like the Milky Way that we're actually in. So if we look at the Hubble classification system, again, more details elsewhere in other videos, but this is kind of like the Hubble tuning fork, or there's a whole variety of different names for this basically, but it helps us understand or helps us classify galaxies visually. Now on the right hand side there, you've kind of got two branches. You've got your spirals, and the normal spirals are at the top and the barred spirals are at the bottom, and actually sometimes you may have an intermediate one. And this is where the central part is not quite got a spherical bulge like the top one. It's not quite got a full bar. It's kind of in between. So it's an intermediate spiral galaxy. These are disk-like galaxies, and they will evolve from the right-hand side to the left-hand side. Spirals get more tightly wound, and their gas gets depleted as they form more stars as they age. On the other side, you've got your ellipticals, and these are classified purely on their shape. So they could be basically round or spherical or more cigar shaped. And actually the E7, those ones that are more cigar shaped, they might not actually be elliptical galaxies, but again, I've got another video on those. They might actually be lenticulars, which are disc-like galaxies, which are they're much older spirals which have lost their spiral arms basically. So these are more spherical shaped. They don't have the spiral arms. They've got less gas content in, and they're older galaxies. So you've got your basic galaxy types. Now some galaxies actually have active black holes in their center. So most galaxies actually have these supermassive black holes in their center, and some of those are actually active, and most of the time they're kind of dormant. They just sit there in the center of the galaxy. We can't really see them, but we do know that they're there. But some of them are actually feeding, so they're actively taking material in, and they become active, and we get what you can see there basically. So in the first yellow square box in the right hand side is actually kind of zoomed in on the galaxy. So the galaxy is actually a very small part, and the black hole is even smaller in the center of that. And if you look to the right hand side with the green box, you've kind of got this black hole, it's got a disk around it. All that material is falling onto the disk, and it creates these enormous powerful jets that's perpendicular to your disk. So if we look at it in a bit more detail, so blazars then, these are powered by the supermassive black hole in the center that's active, and they kind of create these really powerful jets. So you actually have a look, you zoom in a little bit further, and they have these hot accretion disks. So what that means is you've got this disk of material which is spiraling inwards onto the black hole. So it's falling onto the black hole. The black hole is growing in size, it's feeding, it's active. And then what you then get is it then emits these high energy jets which are perpendicular to that disk. It's really high energy jets coming out from the poles of the black hole. So we're assuming actually that the black holes are rotating as well. and the disk is likely to be in the same plane, although that's not always the case. It can be slightly inclined and it makes the jets kind of wander. But again, that's not the purpose of this particular video. So you've got these really powerful jets being emitted, and remember, this is all in the very center part of an enormous, well, not necessarily enormous galaxy, but galaxies are very big compared to stars anyway. So these jets themselves can actually extend hundreds of thousands of light years away from the actual galaxy. And if you were to look at the galaxy in optical light, we would just see the galaxy, which is kind of like that zoomed in section. If you look kind of in the radio part of the spectrum, you typically see these really big radio jets and lobes, which is what's highlighted here, and they can be significantly larger than the galaxy itself. So this black hole is creating structures much, much larger than the galaxy that it actually resides in. So very powerful objects, these supermassive black holes. And that then becomes we call it an AGN, which is an active galactic nuclei. And this is another image here where you've kind of got the jets and I've got another galaxy kind of edge on, and you can see those jets that are emanating kind of perpendicular to the actual galaxy plane as well. So we then have quasars and blazars. Now, blazars are when those jets are directed straight at Earth. So if we look at one of these supermassive black holes emitting these jets, the jet's coming directly at us. A quasar is if it's at a slight angle, so the jets are still there, but they're not directed straight to Earth. And what happens there is the blazar appears a lot more energetic because it's firing that jet straight at us, whereas the quasar is not going directly to Earth. So blazars are always more powerful, or appear more energetic and powerful than a quasar. So yeah, so this one here you've got is likely going to be a quasar because we can see the jets coming out, but with the blazar we wouldn't see those jets directly. It would be beamed, essentially line of sight to us, and they will always appear more energetic. And because of that, it means we can see them at enormous distances, and the most distant one that we have is about 13 billion light years away, because it's so powerful, so energetic, that we can pick it up at such an enormous distance. Some of the most distant objects we've seen in the universe are blazars. Now, onto the microblazars and the microquasars. Now, they're basically the same thing. So you've got a black hole, it's got an accretion disk, it's got jets. But the main difference here is it's just smaller. So it's not a supermassive black hole this time round. This time round, it's stellar size. So what do we mean by that? Well, it's kind of the size or mass of a star. So a considerably smaller, less massive black hole is responsible for a microquasar or a microblazar. And quite often what's happening here is you've got a binary system, you've got a black hole, and then it's got a companion star. And it's pulling material off that companion star, creating a disk around the black hole, and then you've got the same mechanism as what you would have with your supermassive black hole in the center of the galaxy. Accretion disk, material falls onto the black hole, you then get those jets emitted perpendicular to that, but they're much smaller, and they're obviously going to be less powerful than a true blazar or quasar. So in the same way that we have blazars and quasars, it's down to orientation with regards to the microquasar and the microblazar. So a microblazar is going to be directed directly at us. The jets are going to come straight to us. Microquasar, they're slightly off at an angle where we can possibly see the jet, but we don't get it beamed directly to us. So exactly the same sort of configuration. We're just looking at a smaller system this time round. So what are the same, well, okay, not the same, what are the differences then between your blazars, quasars, and then your micro versions of those? Well, with blazars and quasars, these are extremely large. They're going to be on the order of galactic size. And we saw with the images of the jets that those jets can be much larger than a galaxy. So these are enormous, extremely large objects. Well, I say the black holes themselves are not necessarily large in like physical size, but they're large in mass. And they then create those jets, which are enormous. They're typically at the center of a galaxy, so it's going to be those supermassive black holes in the center of a galaxy, and the jets are going to be well in excess of thousands of light years long, depending on how long it's been active for. These are going to be, thousands and thousands of light years long, and they can be billions of light years away, which we saw. Very powerful, very energetic. We can see them a long way off because of that. And they do actually have variability, so they're not always the same power. They can vary in output depending on the material that's falling on them, if anything kind of obstructs it, that sort of thing. But because they're much, much larger objects, the rate of change of that variability is quite slow, and it can be on the order of years, basically. Now, with the microblazars and microquasars, these are typically quite small. So you're talking on the order of star size, star mass. They're not necessarily in the center of a galaxy. These are going to be within a galaxy somewhere, a bit like the stars in and around a galaxy. They could be within our own Milky Way, or they might be in a nearby galaxy. And that's kind of quite important because they're not quite as powerful. We can't see them at such large distances. So they're typically going to have much smaller jets. These jets are going to be on the order of light years as opposed to thousands of light years. Again, it kind of makes sense. Much smaller objects, they're less powerful, the jets are going to be much smaller and much closer. So you're looking on the order of just, maybe thousands of light years away instead of it being billions of light years away. So much closer, just because they're smaller. Doesn't mean that they're not located further distances, just means we likely can't see them because they're just not quite as energetic. And lastly, their variability can be quite fast. Because they're quite small, they can vary in their output quite quickly. Those jets can move, they become misaligned, they have much smaller accretion disks, and they can vary on the order of seconds to days. So these have much faster variability than their much larger companions, the blazars and the quasars. So, thank you for watching. If you enjoy the videos or find them helpful, then do consider becoming a member of the channel. It obviously helps support the channel, but there's also extra videos in the member section as well. So thank you for watching.